am Narendra Kumar, pursuing my PhD in Mechanical Department at IIT Jodhpur under the supervision of Dr. Pradhyut Ranjan Chakrabarti. He is the head of Mechanical Department at IIT Jodhpur. So today here we are talking about this Cascaded latent heat storage system for high temperature CSP applications. So this is our experimental setup here. These are heat exchangers. So we are using cascading system. So we are using here three different type of heat exchangers. These are cell and tube type heat exchangers, and these three are that stainless steel containers. This is having some 20 kilowatt heaters, heat transfer fluids, and that is for the circulation of that HTF. And this is the canned motor pump, this part. So this is generally used for the high temperature fluids to flow throughout the systems. And these are some measuring instruments. This is a pressure transmitter. This is also the pressure transmitter. So we are going to measure the pressure loss due to these pipings and due to these bands. And this is the rotameter to calculate that mass flow rate. What is the mass flow rate during this entire circuit will take place. This is for that after the charging process, all of the HTF will be stored in this second stainless steel container. So we are going to store that latent heat in these heat exchangers. So why there is a need to store that latent heat or that energy in the form of this latent heat? So we know that there is energy degradation or resources depletions are going on due to this. So much energy is using due to the population increasing and all that. So we have to find an alternate solution for that, and that is the clean and renewable energy, like solar energy. So we are focusing on that solar thermal energy. So why there is a need that solar energy to store? Because of this supply and demand mismatch due to intermittent and unreliability of that availability of this solar energy, because this is not available with the same intensity during the whole day. And also we can use that energy during the off-sun hours, like if we have to use that in the night time, or we have to use that during that rainy season and in winter season. So for that we are storing that in the form of the latent heat only. So there are three different type of thermal energy we can store, that thermochemical, sensible and latent. So thermochemical is very tough to control, and it is also a very expensive process. And that sensible, if we talk about the sensible and latent, the latent heat stores more energy with the order of magnitude as compared to that sensible heat. So what is the process of this storing that energy? This is the cell and tube type of heat exchangers. So during the cell side we are taking that phase change materials, and in the tube sides these are some 100 tubes in a single heat exchanger. So total 40 meter length of tubes is there inside this one heat exchanger. So total around 120-130 meter with including these bands are there. In the tube sides we are taking this heat transfer fluids, that is Hytham is we are taking for this experimental. So during the charging process is mainly that the melting of that phase change materials. So for that we will raise the temperature of that HTF with this help of this 20 kilowatt heat exchangers, and we will circulate this HTF from this to this by closing this valve, like with the help of this canned motor pump, to achieve that desired temperature. Like for the charging process, our desired temperature is around 350 degrees centigrade. Its operating temperature is that film temperature is around 370-380 degrees. So for the safer side we are going for 340 or 350 degrees centigrade. So for that, once we reach that 350 or 340 degrees centigrade, so we'll open this valve and we will close this valve. So that HTF will flow through these heat exchangers. So we are using three different type of heat exchangers with three different phase change materials of different melting points. Like for this, the first one we are taking like sodium nitrate, that's melting point is around 308. Second one is solar salt and 220 to 230 degrees centigrade. And for the third one is around 140 degrees centigrade. So for that we can use maximum utilization of the latent heat and that energy of that HTF. So that's why we are using that cascading system. So after that flowing through all these heat exchangers, so this is our second one SS container. So we will store that HTF in this one. So and this whole system, whole piping system and this heat exchangers will be insulated. So we can store that energy in the form of that latent heat. So we can melt that phase change materials, and after, if we have to use that energy, so we can flow, like for CSP application we can flow water, and after coming out of from these 3 heat exchangers, that superheated steams we can get, and also we can use this for this domestic cooking and for that community cooking if we are going to make this on a large scale system. Also we have planned to place that plate system, so we can cook that food, we can hot that plate around 200 or 300 degrees centigrade, and we can cook with the transient flow. If we talk about the moderate temperatures, we can use for process heatings, for that air dryers, for desalination. This was our charging process. So if we talk about the discharging process, so as we stored that heat HTF in this container, so we are having that heat exchanger around 120-140 degrees centigrade, because the melting point of the third one was 140 degrees centigrade. So during the discharging process, we will flow this HTF reversibly, like we move that can pump here and we flow reverse, so we can get that HTF outlet temperature is around 320, 310, around 320 degrees centigrade, and we can use that according to our purpose. So our main focus is that these heat exchangers, as we know that the phase change materials are used for this conversion of this energy, like to melting and solidify this phase change materials, but phase change materials are having very low thermal conductivity. So to enhance that thermal conductivity or that heat transfer, so we can get energy very fast. So we are using CEG in our experiment. So this is expanded graphite. CEG is a compressed expanded graphite. So how this is prepared? So this is prepared by heat treatment process at 900 or 1000 degrees centigrade for 60 seconds. So as this is prepared, so we will compress this expanded graphite in this heat exchangers according to our required porosity, like for 80% or 90%, like we are going to variate this porosity with the help of a compressing mold. So for that preparation of that PCM and CEG, we are having these SS crucibles, and this is a salt bath furnace with the variable temperature. So we will put our phase change materials in the solid form in these crucibles, and these crucibles, with the help of this chain pulley structure, so we are going to put this crucible in this salt bath furnace, and we are going to melt this PCM. So we are having 3 different crucibles for 3 different phase change materials. After this melting process, the soaking process will take place. What is that soaking process? That porous graphite heat exchangers we have prepared. So we will put this whole heat exchangers in this crucibles, like that is having melted PCM. That soaking process take around 30-40 minutes for this soaking of this phase change materials in this porous CEG by that capillary action and that gravity action. After the completion of that soaking process, that fully soaked off this phase change materials in this heat exchanger, so we bring out this heat exchanger from these drums, and then we will clean this whole heat exchangers, and then we will install this in this experimental setup, and we can tight from with of these walls, and we can start our experiment. So this is the main cascaded latent heat storage system. All of these major equipments, and also this measurement instruments, and the preparation of the material and development of that composite PCM for this latent heat storage systems. Thank you.